As I was telling you before, the first fundamental theorem of asset pricing tells us that it is not possible to have an arbitrage on the market if the market is characterized by a risk-neutral measure, which is equivalent to the physical measure. Now, this is very important, and that's why the concept of equivalence in the measures is so relevant for us. And we want to guarantee the fact that when we move from P to Q, or later, we will see that there are also other measures. So Q is the first measure we will play with, but there is, for example, the forward measure, T, that we will use. There is the price measure, D, that we will use, that might be or might not be risk neutral, but still they are very useful. But in any case, they are all equivalent to P, the physical measure. So the first fundamental theorem states the following. If a market M is characterized by a risk-free rate and a risk-neutral measure Q equivalent to the market measure or the physical measure, they are the same, the market measure P, then it allows no arbitrage. So the first fundamental theorem tells us that if we can play with a risk-neutral measure, there is no arbitrage on the market. But it tells us nothing with respect, for example, to the uniqueness of the measure. This is the job of the second fundamental theorem of asset pricing. Okay, so what we do is the following. Consider a portfolio whose value is Vt, such that V0 is equal to 0. And obviously, our T is in the time horizon 0 capital T. But it is always between 0 capital T, unless we specify differently. As I told you, we are always in the same probability space, omega F equal to F capital T P, where the time horizon is 0 capital T. So we have this portfolio. Now, what we know is that our market is characterized by a risk-neutral measure Q. But if Q is the risk-neutral measure and the value of our portfolio is equal to 0 in 0, and this is a fact, so in 0 it is known, it is 0, what do we know? We know that under the risk-neutral measure, 0 needs to be equal to the expectation under Q, the risk-neutral measure, of the discounted value of our portfolio at maturity. Okay, or if you want to rewrite it, E minus RT, there is no randomness in the risk-free rate, the expectation under Q of the capital T. This comes from the fact that Q is the risk-neutral measure. So the value in 0 of the portfolio needs to coincide with the discounted expected value of the portfolio at maturity. And since we know that the value in 0 of the portfolio is 0, this discounted expected value needs to be equal to 0. Now, assume that under P, the probability that V capital T is strictly negative is equal to 0. So, what are we trying to do? We are considering a portfolio whose value in 0 is 0. And now we are telling that for this portfolio, the probability of having a loss as maturity under the physical measure, so under the market measure, is 0. That, if you can remember, is one of the conditions to have an arbitrage. It's the first condition to have an arbitrage. The second one is that the probability then of being positive, strictly positive, is positive. But for sure, we don't want losses. So this is what we require. But what do we know about Q? Q is not only the risk neutral measure, but it is also equivalent to P. So it means that they agree on what is possible and what is not. And so if something has measure 0 under P, needs to have measure 0 under Q. So this is equal to the probability under Q that V capital T is strictly negative. Because of the fact that P and Q are equivalent. Huh? Okay, but given this, we necessarily have that also this needs to be true. So if Q assigns mass 0 to the event loss in the portfolio, negative value for us is a loss at the moment, in risk management it will be the opposite. The negative value is a profit, because in order to model losses and get rid of all the many minus signs that appear in the formula, you switch. So you consider not the profit and loss, but the loss and profit. So losses are positive and profits are negative. But here it's the profit loss. So profits are positive and losses are negative. So a negative portfolio means that essentially at maturity, we have to give money to someone. That for us is a loss. So what happens? If under P we have this event, which is the first condition to have an arbitrage, then it needs to be the same under Q because of the equivalence. But if this is true, then also the fact that I can have a strictly positive portfolio needs to have mass 0 under Q. Because of a simple fact, is that if this is not true, this is not true. Why? So imagine that this fact is not true. So this is false. If this is the case, you agree with me that it will imply that the probability under Q of e to the minus RT, that is a discounted quantity and it's totally deterministic and positive, what we have is that that should also be the case. So if this is not true, then we have this. But if we have this, then you are taking the expectation of something that the maturity can be 0, but also positive. So the expectation cannot be equal to 0. It needs to be positive. But then it means that Q is no longer the risk neutral measure. And we are assuming Q to be the risk neutral measure. So this needs to be true because of the risk neutral measure. And this is true, this cannot be true. Otherwise there is a contradiction. Okay, I repeat, if I assume that under P, the first condition for the existence of an arbitrage is satisfied, it means that I'm saying that at maturity, my portfolio will not generate a loss. So the probability of seeing a loss is 0. But since Q is equivalent to P, that probability is 0 under Q. But Q is the risk-neutral measure, and my portfolio has value in 0 equal to 0, and it corresponds to the discounted expected value of the portfolio at maturity. But the only condition for that to be guaranteed, so for the fact that Q is actually the risk-neutral measure, is that under Q also the fact of having a strict positive profit needs to be 0. In other words, the value of the portfolio at maturity needs to be 0. It cannot be negative, it cannot be positive. Because otherwise, this is contradicted. So we have that these needs to be true and these needs to be false. So we have that Q of B, capital T, being strictly positive is equal to 0. But Q is equivalent to P. So they agree on what has mass 0. So this implies that the probability of BT being positive is equal to 0. So B cannot be an arbitrage. So we start by introducing something that we want to play the role of an arbitrage, but then we immediately see that this is not compatible with the fact that we have the risk-neutral measure. So the existence of the risk-neutral measure guarantees that it's not possible to have the arbitrage on the line. So very briefly, I start from a portfolio, and I state, okay, this portfolio has value 0, in 0. Since the risk-neutral measure is risk-neutral, it means that this 0 needs to correspond to the discounted expected value of the portfolio at maturity, which is this. Now, I assume that that portfolio plays the role of an arbitrage. So I say, okay, under P, under the physical measure, I want the portfolio not to generate losses. But then, since Q is equivalent to P, it needs to be the same also for Q. So under Q, it is not possible to observe a loss. Fine, this is totally fine with what we have written so far. But then, in order to guarantee that this is still true, we also have to impose that we cannot have a profit. Because if we have a profit, then the expectation of something that at maturity is either 0 or positive cannot be 0. It needs to be positive. Maybe very small, but positive, not exactly equal to 0. So the only condition is that it's not possible under Q to observe a profit. And if it is not possible under Q, then it is not possible under P, because P and Q are equivalent. So if I can move from P to Q, and from Q to P is the same. So if we are using behind the scenes a Radon-Nikodym derivative, it is proper because we have that the Radon-Nikodym derivative is strictly positive and expectation 1. As I told you, if you remove the fact that it's strictly positive but just not negative, then it will not be true because they will not be necessarily equivalent. But in this framework, it works. So you see, the proof of the first fundamental theorem of asset pricing is rather simple. Now, for what concerns the second fundamental theorem of asset pricing, at this stage, we just state it, and we don't prove it. We will prove it later because we need an extra tool to prove it. But we already stated because from now on, we will work under the conditions for which the second fundamental theorem of asset pricing guarantees the uniqueness of the risk-neutral measure. And it stays the same, the following. A market M risk-free rate R and risk-neutral measure Q. From now on, we will not tell that, but I stated equivalent to P. Otherwise, we cannot guarantee the first. Okay, so it's always equivalent to the physical measure. A market M with risk-free rate R and risk-neutral measure Q is complete if and only if Q is unique. So the second fundamental theorem of asset pricing tells us that if we have a complete market, and I will tell you in a second what that means, then the risk-neutral measure on the market that I can identify is unique. And in order for the market to be complete, the risk-neutral measure needs to be unique. It's an if and only if. It's a very important theoretical result. Now, what is a complete market? A complete market is some sort of wishful thinking, because it's a market in which every security can be priced and exchanged or traded, and every risk can be hedged. What does it mean? It means that it's an extremely liquid market in which every security can be traded, and for every security it is possible to come out to an evaluation of the price. And already this, you see, is not so true, because we know that the markets are often characterized by liquidity risk, so the fact that actually you are not so able to trade all you want, and also the fact that some products are very difficult, if not impossible, to price. We will say something about CDOs, for example, in due course, or other things. But in any case, we are requiring these things to be priceable and tradable. But even stronger is the requirement that every risk can be hedged. That is to say that if I invest and I create a portfolio that necessarily, otherwise it would be an arbitrage, might generate losses, I can build a strategy to cover for those losses. This is the job of risk management. We will see that, for example, using the grids and other tools, we can cover for market risk. We will see that we can build models to understand the behavior of the probability of default of a counterparty, of the recovery risk embedded in a counterparty, of the loss given default of a counterparty, so credit risk. We will see that we can, in principle, build a portfolio that deals with operational risk, which is another type of risk you can face. But the first thing that I will tell you in risk management is that, unfortunately, you don't have infinite resources. So you will always be in the situations in which you can identify the risk, you might assess the risks, but at a certain point you have to build a ranking of the risks. So you have to prioritize risks because you don't have enough resources to cover for everything. So you will have to choose those ones that you want to cover and accept the other ones. So accept the possible losses of the other ones. So, but if we are in a beautiful setting in which actually we can do whatever we want, we have infinite resources in order to hedge all the risks, there is no liquidity problem, and we can transact, we call this a complete market. A secondary property of a complete market you can imagine is that if all the things I told you are true, it also means that we have complete information, which is another problem. It's not true. But if we are in a beautiful world in which the market is complete, then the risk neutral measure is unique. So the problem for us just becomes the problem of identifying the risk neutral measure. So we have a physical measure. If we can build, as we will do an equivalent measure which is risk neutral, then we have to stop worrying about the fact that it is unique, because the second fundamental theorem of asset pricing guarantees that it is unique. So at that point, we are totally able to build our benchmark price and make our evaluations about the European call, the European put, the American call, the American put, whatever you want, because we have the benchmark. Without this theorem, it could be that we have Q1, Q2, Q3, Q4, and then each one of us can choose one, and we're back to the situations in which there is no unique benchmark we can use to discuss. So for the moment, we jump over the proof of this theorem. But from now on, we are always playing in a complete market. Okay? So for the moment, we have solved the problem of having one and unique risk neutral measure. We have it. The problem is to find it. So we want to find it. So for us, the problem reduces to one thing, to find the proper Radon-Nikodym derivative. So we have seen that the Radon-Nikodym derivative is one of the ways in which I can move from P to Q. I want to find the Radon-Nikodym derivative Z such that I move from P to Q, and Q is risk neutral. Once I've done that, the second fundamental theorem of asset pricing tells me that I can stop. Q is unique. It's the one. There is nothing else. Now, in financial mathematics, there are different families of Radon-Nikodym derivatives. The ones that we will consider together are all those that are in the exponential class. So the exponential martingale and the generalized exponential martingale. What I want to stress is that they are not the only ones. These are the ones that work if you play with the Brownian motion. Okay, since in this course, all the randomness will always be related to the Brownian motion, then these are the Radon-Nikodym derivatives we will play with. If you substitute the Brownian motion with other processes, the Poisson process, or you want to enter in the Lévy framework, then obviously the class of Radon-Nikodym derivatives that you use is different. But for us, it's already complicated as it is now. Now, the first class of Radon-Nikodym derivatives that I want to introduce is the basic exponential martingale class. Now, there are different ways in which you can introduce this class. I prefer to do that in the following. We introduce the class per se, as they were just a collection of random variables. We study the properties very briefly, and we show that this class of random variables, so this stochastic process, is a process that allows, using a fundamental theorem that goes under the name of Cameron-Martin, to play with the drift of the Brownian motion. So we will see that thanks to the exponential martingale and the Cameron-Martin theorem, we can find a connection between a Brownian motion and a Brownian motion with drift. We will start by considering, for example, a Brownian motion with drift, where the drift will be later the drift we want to remove, under the physical measure, and we want to find another measure that for us will be the risk neutral measure, in which the law of the Brownian motion with drift is exactly the same law of a standard Brownian motion under the other measure. So it simplifies things a lot. We are getting rid of the drift. In probabilistic terms, we have the same object, just changing the measure, and we get rid of the drift. We will see that this block of knowledge that we are building now will immediately fit within the Black-Scholes-Merton framework. And ex post, you will see how this exponential martingale class is obtained. It's not that someone one morning woke up and started trying exponential martingales. It comes quite naturally from the Black-Scholes-Merton framework. But since we want to study the properties because we need them, it's better to isolate them for a bit and then put them into the context instead of introducing the concept, stop to study the properties and continuing. Now, this is what we call the exponential martingale. Z psi t is equal to the exponential of psi bt minus psi squared t over 2. This is what we call exponential martingale. Now, what we want to prove is that this object is actually a martingale. So I already tell you that it's called the exponential martingale. But what we want to show is that it is actually a martingale and that it can be a Radon-Nikodym derivative. Now, the fact that it needs to be a Radon-Nikodym derivative comes from the fact that it will be the tool we use to move from P to Q and from Q to P by taking 1 over. But the things that we have to check are very simple. The first one is that it is always positive, and the second is that it has expectation equal to 1. Okay, these are the basic things we want to check to verify it can be, for a given t, a Radon-Nikodym derivative. After that, we can also show that it is a martingale. So if you remember what I told you about connections of Radon-Nikodym derivatives obtained by taking the conditional expectation with respect to the filtration, we will have a collection of Radon-Nikodym derivatives that builds a martingale, and so it can be used as the process we were looking for. Now, let's see that this is it a candidate for the Radon-Nikodym? Now, we have to check that it is positive, and I hope you agree with me that this is positive. It's the exponential of something, so the fact that it's positive, it's obvious. And we want to compute the expectation, and we want this expectation to be equal to 1. Now, for the first time, so please pay attention, because to show that this is to show that this quantity is equal to 1 in expectation is simple, is extremely simple, but it relies on one thing that maybe you know, maybe you don't. And if you don't know it, please know it now, because we will use that over and over and over and over again in the rest of the course. It's a stupid thing, but if you don't understand this, then it's a problem for the rest of the course. So let's compute this expectation, and we want this expectation to be equal to 1. Okay, this is what we want to show, that this expectation is equal to 1. Okay, let's compute this expectation. What I can do, I can just substitute my definition of z. So it's the exponential of psi bt minus psi squared t over 2. Okay? Now, And by the way, just to be pedantic, but it's important, we are playing under P here, okay? Because remember that when we introduce the Radon-Nikodym derivative to move from P to Q, we want the expectation to be equal to 1 for the random variable Z under P, okay? So even if for the moment is not so relevant, remember that we are playing under P. Now, you agree with me that in this quantity here, the only source of randomness is our Brownian motion, okay? It's the only one. This quantity here is a parameter, so we know it, and this quantity here is known, okay? So there is no randomness. What I can do is to rewrite that. I do all the steps, even if they are not particularly complicated. I can rewrite these as the product of two exponentials. The exponential of this part and the exponential of this part. Okay? So now this part is deterministic. It can go out of the exponential. So I just write the exponential, of the expectation of the exponential. The exponential stays there. So x2 over 2. Okay? And now we have the expectation of the exponential of psi bt. Little digression. This is what we have to know. What do I know about bt? Bt is a Brownian motion. Okay? So, what do I know about the increments of the Brownian motion? They are normally distributed with mean 0 and variance equal to the length of the time increment. So in that specific case, that guy there, bt, we can take the increment with respect to b0, so the time 0. So it's a random variable which is normally distributed with mean 0 and variance t. So let's x be a random variable which is normally distributed with mean, mu, and standard deviation sigma. Or if you prefer to write that in terms of variance, sigma squared. Totally the same. Okay? So this is the standard deviation. What happens if I exponentiate x? So I take e of x, or just to be consistent with our notation, exp of x. What is this? It's still a random variable, but what's the distribution of this random variable? Is it normal?
Log.
It's log normal. It's exactly log normal. It's log normal of parameter mu and sigma. But here, there is something very important to recall. If I start from my x, what is the expectation of x? It's mu. It's a normal. And what is the variance of x? Sigma squared. Okay? But what is the expectation of these? It is not mu. It is not mu. It is the exponential of mu plus sigma squared over 2. That's the expectation of the log normal. So be careful, because in the log normal, and this is a very common error, apart from this course. Since most people are used to the fact that for the normal, the mean is equal to mu and the variance is sigma squared, and these are the parameters that define the normal, then the mean of the log normal is mu. No. The mean and the variance of the log normal are both influenced by the parameters mu and sigma that are no longer the moments. The moments are functions of those parameters. Okay, So this is the expectation. And last thing that we will exploit, the variance, we will be back when we need it, okay? But also the variance obviously is not sigma squared. It is the exponential of sigma squared times the exponential of minus 1 and blah, blah, blah. But another thing, if x is my normal random variable, okay? It's true in general, but since we are playing with x, let's play with the normal random variable. We know that the variance of x is sigma squared. Fine. And if I consider ax, what's the variance of ax?
A squared.
Yeah, good. A squared sigma squared. Okay? Now, this is all you have to remember this, and now this becomes trivial. Why? The first part remains the same. So it's the exponential of minus sine squared divided by 2t. And now we have this expectation. Now, this is the expectation of a normally distributed random variable with mean 0 and standard deviation square root of t. So what's the mean? 0 t. Okay? But we are also multiplying by a constant, psi. So we are in this framework. So the variance becomes the exponential of psi squared, our a squared, the variance t divided by 2. Okay. So this is the exponential of minus psi squared over 2t. This is the exponential of psi squared t over 2. The only difference is that one is a minus sign and the other no. So they compensate. It's the exponential of 0, which is 1. Okay? So it's very, very, very important that you recall these. It's e to the power mu plus sigma squared over 2. This is the expected value of a log normally distributed random variable of parameters mu and sigma, or sigma squared. I repeat, it's totally irrelevant. But it's very important that you recall that this is the expected value. Then, for us, the expected value of our random variable, which is normally distributed, which is the Brownian motion, is always 0. So the mu part disappears. And we remain with this. The variance is just the length of the time interval, so it's t. If it is multiplied by a constant like psi in this situation, it will be psi squared t, and then we divide by 2. Okay, that's the expectation. And it guarantees that actually it is it can play the role of a Radon-Nikodym derivative. It is positive, trivial because it's an exponential, and it is expectation equal to 1. Okay, this is all we have to prove in order to say that this is, in principle, a Radon-Nikodym derivative. Later, we will show that it's also the one that generates the risk neutral, but it can be used. Now, what we want to show now is that it is also martingale. So in this course, we will play always with transformations of normal random variables. So we take the exponentiation of the normal and we get log normal. We take the square of a standard normal and we get the chi-square. we take the sum of squares of normals and we get the f. Once we have the log normal, we can exploit the properties of the log normal, and these are very important. Because if I tell you for a moment that this is already our final Radon-Nikodym derivative, what we know that this guy here is a log normal random variable. If I fix t, this is a log normal random variable. We have just showed that, okay? Because the only randomness is a normal, and we take the exponential. But a nice property, an extremely useful property of the log normal random variable is that if I know that x is log normal, what I know about x to the minus 1? So 1 over x. It is still log normal. Consider two-time instance, t and s, positive. What I want to show, because it simplifies a lot notation, is the following. If I take z of t plus s, okay, and I take the expectation of this guy stopped at time s, this is equal to z psi of s. Okay, so this is what I want to show. Okay, so how can I show that? I just substitute, so let me cancel this for a second. This is what we want to show. I just substitute the definition of my z. Okay, so the definition of my z is this. So it's the expectation of the exponential, thank you very much, of psi b t plus s minus psi squared t plus s divided by 2, f of s, and now I should have, now we have everything. Okay, so this is what I'm doing, just rewriting the definition. Now, one thing that I can do is the following. I will add and remove one object inside my formula, which is the standard way. You probably remember when you proved that the Brownian motion is a martingale with respect to its natural filtration. This is what you did. You add and remove BS, BT, depending on the letter that you were using. We do exactly the same. So now, here, the step that we do is to add or remove psi BS inside our exponential. I can rearrange all the terms, okay? So, minus psi squared t over 2 minus psi squared s over 2. Close the parentheses, condition on fs, and we're done. Okay. I just take 2 extra minutes of your time, but then we close. Okay, so now look at this. Start observing things. This is an increment of the Brownian motion, okay? Times psi, but it's not important. This is an increment of the Brownian motion. And it's t plus s minus s. So it's in the future with respect to s. First thing to recall. Second thing, if I take these, I can combine these with this term. How? So again, allow me to isolate the increment of the Brownian motion. So this is the exponential of psi b t plus s minus bs. Okay, and this is the first thing that multiplies another exponential, which is the exponential that takes into account psi bs minus xi square s over 2 times the exponential of minus xi square t over 2. Everything here condition on fs. Okay? So I'm just rearranging the terms here and splitting the exponential into the product of the exponentials. Fine. Now, the first thing that I can notice is that this quantity here, you will agree with me, is equal to what? Is equal to z psi of s. Okay? And what happens when we are in S? Because of the measurability, this quantity goes out of the expectation. Okay? So this is z psi s, the expectation of what? Of exp of psi b t plus s minus bs, closed, closed. And then another thing that I can do is the following. I can close the expectation here because of one simple observation, is that now this quantity here is deterministic. Okay, so I can write that outside of the expectation. Fine. But now there is another thing that I can notice, and it's the following. So this term remains there. I take this term in front of the expectation. And now look at the expectation here. This is the future increment of a Brownian motion with respect to time s. Okay, so what do I know about the future increments? They're independent because it's non-anticipating. Okay, so I can get rid of this quantity here. So I can remove the conditioning with respect to the sigma alpha. Fine, but then what I have here, this is the expectation of the exponential of a quantity, this one, which is a random variable, which is normally distributed with mean 0 and variance t plus s minus s. Okay, because it's the increment of the time interval. T plus s minus s, so it's t. So the variance, if you want the standard deviation to be consistent with my notation in square root of t, the variance is t. Will it be a surprise that this guy here is exactly this guy with a change of sign? No, because we are using the fact that it's the expectation of a log normally distributed random variable. So this is the expectation, the exponential of xi squared t over 2. And these two guys simplify each other. So what remains is this. So it's a martingale. So we have a collection of Radon-Nikodym derivative. If I fix t, these are log-normally distributed random variables that are positive. Expectation 1, very good. And then if I consider them together, they also represent a martingale with respect to what? I was not telling that before, but it should be evident. The measure is p, because we always take the expectation with respect to p in defining z. And with respect to what? We need a filtration. So, but what is f? As I told you, it is the natural filtration generated by the price process or the Brownian motion. In this situation, the price process is not yet there. We just have the Brownian motion. So ft is the natural filtration generated by the Brownian motion. So what we have is that we have proven that these are Radon-Nikodym derivatives. They are martingales. And next time, we will see that if I have a Brownian motion with drift, I can move under P, for example, I can move to another measure Q, in which this guy has the same law of this guy, a standard Brownian motion. So I can get rid of this. I don't want that. I just want to remove the drift because the drift depends on expectations of people, and I don't want to play with that. Okay, so we continue next week.